Hello and welcome to Anton Math. Now in this video we're going to be kicking off our section on elementary number theory. And we're not going to get super deep into number theory, but we're going to give you kind of a taste of what's going on for those of you interested in going into a number theory course. Now in general, number theory is the study of integers, the study of relationships between integers. There's a huge focus on primes and modular arithmetic, and really all we're going to be talking about is those two things that I just mentioned, mostly primes and modular arithmetic. Now there's a lot of relationship between primes and modular arithmetic, as we're going to see. But first we're going to talk about primes, and in these next couple of videos we're going to be talking about the GCD, which is going to be very helpful once we start getting into modular arithmetic. Now in the preliminary section for this course, we talked about primes and factors and all that, but just for a quick review, recall that an integer a is a multiple of an integer b if there exists an integer c such that a equals bc. So in other words, a is a multiple of b if I can multiply b by an integer and get a. We say b and c are divisors of a, and if b or c are positive, we call it a factor of a. And if b and c are both positive, then they're both going to be factors of a. In other words, factors are just positive divisors. It's a different word for a positive divisor. Now a prime number p is a positive integer other than 1 that has no factors other than 1 and p. Now notice I say no factors because of course every number is going to have more divisors than 1 and p because it's going to have -1 and -p as divisors. But -1 and -p are not factors, so we're okay there, right? Now the integers themselves are made up of 4 classes. We have the 0, which of course is 0, the units 1 and -1, and a unit just means that it has a multiplicative inverse. And we're not going to get into that right now, but in the next section when we start talking about modular arithmetic, we'll talk more about what a multiplicative inverse means. We have the primes, and we have the composites, which is basically everything else not in those first 3 categories. You could think of composites as numbers that could be factored into multiple primes. Now we have what's called the fundamental theorem of arithmetic, if you recall this from our preliminaries. The fundamental theorem of arithmetic, sometimes called the unique factorization theorem, says that every positive integer can be expressed uniquely as a product of its prime factors up to reordering. Right? So let's have an example of this. All that this is saying is if I have some number like 48, I can factor 48 uniquely up to reordering. And what that means, uniquely up to reordering, that just means that if I change the order of the factors, that's still the same factorization. All we're concerned with are the actual factors themselves. So let's take a look. Now 48, we can of course do it in long steps. I'm just going to take it step by step. I know 48 is divisible by 2, so I can write 48 as 2 times 24. Now 2 is prime, so I'm done with this 2. But 24 is not prime and is divisible by 2 again. So I can write this as 2 squared times 12, right? What I've done is I've written 24 as 2 times 12, and I just have a 2 squared because I already had a 2. Now again, the 2's are prime, but the 12 is not, so I'm going to divide by 2 again, and I get 2 cubed times 6. And of course 6 is just 2 times 3, so that's going to give me 2 to the 4th times 3. Now this is our prime factorization. Both 2 and 3 are primes. No other integers divide 2 and 3 other than themselves and 1. And the up to reordering just means that if I wrote this as, I don't know, for example, 2 times 3 times 2 cubed, this would be the same factorization. We consider this the same unique factorization, right? This is just a reordering, which we're not concerned with. Now we can see here that if 1 was a prime, we said in our definition before that 1 was not a prime. If 1 was a prime, we might get into trouble because, for example, 6 equals 2 times 3. It also equals 1 times 2 times 3. And it also equals 1 squared times 2 times 3. Now these 3 representations of 6 are not unique, they're not reordered unique factorizations. They're actually different, right? Here I have a factor of 1, here I have a factor of 1 squared, etc. But 1's not prime, so this doesn't really matter. Here we're still just looking at the prime factorization of 2, 3, and we always exclude the 1's in this case. Now sometimes when we're doing this prime factorization, we'll come across a number, and we're not sure if that number's prime or if it's composite. And we want to be able to know whether a number's prime or composite, because if it's prime, then we're done with that number. Like when we reached this first 2, I knew 2 was prime, so I don't have to factor 2 anymore. But 24 is composite, so I know I have to factor it more. So how do we know if a large number is prime or composite? Well, in general, we can't know just by looking at it. but there is some helpfulness here that I'm going to share with you. If we're going to test whether a number is prime, we only need to check for positive prime factors less than or equal to the square root of n. So for example, if I'm looking at the number 59 and I want to know whether or not the number 59 is prime, I just need to see, well, 2 doesn't divide 59, 3 doesn't divide 59. And I know that because if 3 divided it, then I'd have 9 plus 5 would be divisible by 3. Hopefully you all know that trick. If you add all the digits of a number together, if that sum is divisible by 3, then the number itself is also divisible by 3. So 3 does not divide 59 because 9 plus 5 is 14. 2 doesn't divide 59, so 4 doesn't divide 59. But what's wrong with this? I did an extra step here, didn't I? I only need to check for positive prime factors. So this is an unnecessary auxiliary step, right? Now 5 doesn't divide 59. I don't need to check 6 because again it's not a prime factor. 7 doesn't divide 59. And we're done, right? 8 squared is 64. 64 is bigger than 59, so the square root of 59 is less than 8. So I've checked everything that's less than or equal to square root of 59. Now, why is this sufficient? Why am I done here? Well, let's just say that 59 equals a times b. Let's say that it does factor, right? And let's say that a is greater than the square root of 59. So I'm like, well, if I need to find this factor a, that means I need to go past the square root of 59, don't I? But if a is greater than the square root of 59, that's going to imply that b is less than the square root of 59, right? If b was greater than or equal to the square root of 59, then a times b would be greater than 59, right? So I only need to check everything up to the square root of 59. After that, if I didn't find anything in those first several primes, it means that there's nothing else complement to those in the next 40 or so numbers. Now that's the basics of primes and divisors. In the next video, we're going to talk about GCD and the Euclidean algorithm. We'll see you there.